Good afternoon, everyone. Welcome to the second lecture in the week 3 of this course, Principles of Modern CDMA, MIMO, OFDM Wireless Communication. So today we are going to discuss some questions based on the week 3, and also we are going to discuss some concepts of wireless channel and the delay spread. So these things, first we will discuss some concepts, then we are going to solve the questions of week 3. And this video will be recorded and it will be uploaded on YouTube. And the link will be shared in the NPTEL portal. So today we are going to study about wireless channel. Like previously we have studied that the fading wireless channel comprises several components, like multipath components, that is arising from the presence of like non-line of sight signal propagation path, and these non-line of sight components arise from the scattering effects of the objects in the wireless environment, such that it can be scattered by buildings, trees, vehicles, water bodies, etc. So in today's class we will study about the nature of this wireless channel, and also like with respect to the properties such as inter-symbol interference and time varying characteristics. So let's suppose like the impulse response of the standard multipath wireless channel ht was given as we have studied previously, I is equal to 0 to L minus 1, So maybe the internet speed may be slow. The impulse response of the standard multipath wireless channel is modeled as ht is equal to ai. This is the attenuation constant del of impulse function of t minus tau I. So here tau I is the delay. So now this tau I is delaying the signal by tau I. Okay. Sorry for the delay due to the internet, due to the power cut. So AI is the attenuation associated with ith component. Now L denotes the total number of paths or multipath components. So like from this equation of impulse response of this channel, we can also write the power profile. So the multipath power profile, power will be a square of this amplitude. Multipath power profile of the channel is denoted by phi t. Phi t is equal to summation I is equal to 0 to L minus 1. It is the power, so we will do the mod of ai square del of t minus tau I. So this is our power profile, and we can also take it as g of I. G of I is equal to mod of del I square. So done. So we can also draw, let's suppose L is equal to 5. So we can draw the gain of the multipath channel. So that we can draw like this. So this is our x-axis with tau. So let's suppose that t is equal to tau naught. The first multipath signal arrives. So this is our G naught. G naught will be here, A naught mod square. Now at t is equal to tau 1, this will be Z1 is equal to A1 square. So like this we can draw. So for L is equal to 5, this is a power profile of the multipath channel. So here you can see that signal first first signal arrived at t is equal to tau naught and last signal arrived at t is equal to tau 4. So we have to find the now the spread, delay spread. So the complete delay spread will be from tau naught to tau 4. So this is the delay spread. And also we can draw the make a table like this is a path gain and the delay. So at the delay of tau naught, the path gain was A naught square. Delay of tau 1, the path gain was A1 mod square. From this graph, we can draw this table. So this is the gain and delay. Like at what delay, what was the gain? So the complete delay spread, let's denote it by sigma t. So the delay spread of a wireless channel is a key parameter that characterizes the nature of the wireless environment and is denoted by the parameter sigma t here. We like we have to now compute the delay spread parameter sigma t of the wireless channel. So what is the max? The first is the maximum delay spread. So this is denoted as sigma t max. So sigma t max, what it will be? Let's suppose there are L components. We will write here. Let's suppose there are L multipath components. So if there are L multipath components, so the Lth components arrived at tau of L minus 1, and the first component arrived at tau of 0. So sigma t max, that is the maximum delay spread, that will be equal to tau of L minus 1 minus tau of 0. Okay, so this is our maximum delay spread. So this is just the difference between the last signal arrived from the first signal arrived. It is the interval between the arrival of the first and last signal at the receiver. So now let's suppose, like in the previous example, let's take an example. Consider L is equal to 5 and T of L minus 1, that is the last arriving path, is equal to 5 microsecond, and tau naught, that is the first arriving path, is equal to 0 microseconds. So find the maximum delay spread. So in this question, the maximum delay spread will be tau of L minus 1 minus tau of tau naught. So it will be 5 minus 0 microsecond. This will be equal to 5 microsecond. But there is one problem with this, like when we are finding the maximum delay spread, so the problem occurs. Let's suppose there are L multipaths, and the first one arrived at tau naught is this, and at the end, let's suppose the paths which arrived at the end have very low power. So these paths which arrived later are having significantly low power. Due to the, it can be because of the larger propagation distance or the weaker reflection. So now, so these result in very large value of the maximum delay spread. Now here if you find the maximum delay spread, like here we have find sigma t max equal to tau of L minus 1 minus tau naught. So the maximum delay spread will be very large here. So this is the maximum delay spread in this case. But the last paths, like the last many paths, that is having a very negligible power, and the maximum delay spread metric is not reliable indicator of the true power spread of the arriving multipath signal components. Like here we can say that sigma t max is not the reliable indicator of the true power spread of the multipath signal components. Why? Because these components are very weak in power, and but it takes time to arrive. So for this, what we can do, we can take the weighted delays. Weighted delays means we will like add the signal power in the multipath components, and this is known as the like RMS delay spread. So when we weight the delay of the signal components with respect to the power in the arriving path, it is not susceptible to the distortion in the scenarios with large number of trailing weak components. So now we will study the RMS delay spread. So this is denoted as sigma t RMS. So what does RMS delay spread do? It wakes the signal components with respect to the power in the arriving path. So here we can see these paths we have to not consider weak paths of low power. So if we weighs the delay with respect to the power of the signal, then these paths can be eliminated. For this, we will take a term, new quantity, that is Bi is equal to mod AI square divided by This can be also written as Gi by G naught G1 plus G of L minus 1. So this is our new quantity. So here Gi denotes the total power corresponding to the ith path. So Gi is our total power of the ith path. And this summation denotes the total power in the multipath power profile. So now, so basically Bi is the ratio of power of the ith path divided by total power of the multipath. Also the summation of Bi, what it will be? Summation of Bi will be summation of Gi divided by G naught plus G1 dot, or we can take this as a total power. This is a constant term, L minus 1. So now when we do the summation, we will get G naught plus G1 dot plus G of L minus 1 divided by total power. And also like PT is equal to basically G naught plus G1 plus G of L minus 1. So this term will be equal to 1. So summation of Bi will be equal to 1. So B naught plus B1 plus B2 B of L minus 1 is equal to 1. So now we have to find first the average delay. So then we will find the RMS delay. So average delay, let's denote by tau bar, is given as B naught tau naught B1 tau 1 plus B of L minus 1 tau of L minus 1. So this is equal to summation of I is equal to 0 to L minus 1 Bi tau I. So this we can write as Bi can be Gi divided by summation of j is equal to 0 to L minus 1 G of j and tau I. So this is our average delay. This formula is for finding the average delay. Now our aim was to find the RMS delay spread. So now here you can see that the average delay is found by the weighting the parameter delay tau I, weighting the parameter delay tau I with respect to the power, that is Gi. So we have used the Gi term to weight and find the average delay. Now the RMS delay can be found as B naught tau naught minus tau bar square plus B1 tau 1 minus tau bar square, so on, b of L minus 1, tau of L minus 1 minus tau bar square. So this is given as summation of I is equal to 0 to L minus 1 bi. We can give this equation like this. So our RMS delay spread will be square root of now this bi we can again write it as I is equal to 0 to L minus 1 gi tau I minus tau bar square divided by summation of gi. I is equal to 0 to L minus 1. And also when you write in terms of A, the equation will be I is equal to 0 to L minus 1. Gi is basically AI mod square, that is the power of the ith component, tau I minus tau bar square divided by summation of I is equal to 0 to L minus 1 mod of AI square. So this is the formula of RMS delay spread. Okay. So now we will solve the question. Before that, we will summarize everything till now what we have studied. So first one we have studied, that is the maximum delay spread. So maximum delay spread is given as the delay of the lth component, lth multipath component minus the first multipath component. Second, we studied is the average delay spread. That can be given as this is the average delay spread. Now the third thing we studied is the RMS, root mean square delay spread. So this is given as so this is the formula of the root mean square delay spread. So now let's solve a question, and after that we'll solve the question of the assignment 3. So L is equal to 4 multipath components is given, and the power profile of this L is equal to 4 multipath components are given. So this is 0 dB. Y-axis is the like gives the power of the each multipath component. This is minus 10 dB, and this is minus 20 dB. And the first signal arrives at tau naught, that is given in here microsecond. So this is 0 microsecond. The next is 1 microsecond. This one is 3 microsecond, and this is 5 microsecond. So this is the power profile given. So now we have to compute the RMS delay spread. Sigma T RMS for this wireless channel. So we will use this formula, but for computing RMS delay spread, it requires also the average delay spread, because here you can see this formula requires tau bar. So we have to compute the average delay spread as well. Now we have to first compute all the powers in the normal unit as it is given in dB. So the first path arrived at 0 microsecond, and power is minus 20 dB. So G naught is equal to minus 20 dB, because power is mod of A naught square, that is G naught. Now 10 log 10 G naught is equal to, or we can directly write in terms of A, or we can write in G naught. So G naught is equal to minus 20. So by this we will get G naught is equal to 10 to the power of minus 2, that is equal to 0.01. But G naught is mod of A naught squared. So A naught is square root of G. So is implied that A naught is equal to square root of G naught. So that will be equal to 0.1. Okay. Now for the second path we will find 10 log 10 G1, that is given as here. G1 is given as, this is G naught, G1, G2 and G3. So G1 is given as minus 10 dB. So G1 is equal to 10 to the power of minus 1, that is equal to 0.1. Okay, so now A1 is equal to square root of G1, so that will be equal to square root of 0.1 is 0.3162. Now coming to the third path, so this is given as 0 dB. So G2 is equal to 0 dB. So 10 log 10 G2 is equal to 0 is imply that Z2 is equal to 10 to the power of 0, that is equal to 1, and A2 will be also a square root of G2, it will be 1. Now coming to the fourth path, that is again given as minus 10 dB. For minus 10 dB we have already calculated G3 is equal to minus 10 dB, so we will get G3 is equal to in the second path we have already calculated for minus 10 dB, so it will be G3 is equal to 0.1 and A3 is equal to 0.3162. So now we can give the gain table here for the simplicity. First column represents tau, that is the delay. Second, dB, gain in dB. Third, G, and fourth is A, that is equal to square root of G. The first component arrived at 0 microsecond. It was given minus 20 dB. And what was the G value we have calculated? 0.01 and A is 0.1. Second component arrived at 1 microsecond. dB gain was minus 10 dB and G was 0. A was 0.3160 and G was 0.1. 0.3162. Now the third component arrived at tau is equal to 3 microsecond. So in this the dB gain was given as 0 and G was 1, A was 1. And the fourth component arrived at 5 microsecond. And the gain was again minus 10 dB. So G was 0.1 and A was 0.3162. So this is the gain table. So now we have to find, first we will find the average delay. That is given as tau bar. So tau bar is summation of the formula we will use Gi tau I divided by summation of Gi. So G naught tau naught, how much it is? 0.01 into 0. G1 tau 1 0.1 into 1 plus G2 into tau 2 1 into 3 plus 0.1 into 5. Okay, divided by summation of Gi. So that is 0.01 plus 0.1 plus 1 plus 0.1. So the average delay spread, that is equal to, this will be in microsecond, 3.6 divided by 1.21. So after division we will get, so this is our average delay spread. Now we will use this tau bar to find the RMS delay spread. This is equal to the summation of the square root of so this is our RMS delay spread. So we will use the formula and find. So in this case, it will be GI is 0.01 into TI. 0 minus tau bar is 2.9752 squared plus GI is 0.1. Tau is 1 minus 2.9752 squared plus GI is 1 into 3 minus 2.9752 squared plus 0.1 into 5 minus 2.9752 squared divided by 0.01 plus 0.1 plus 1 plus 0.1. So when we simplify this, answer we will get as 0.09. So the final answer will get as 0.8573 microsecond. So the RMS delay spread is 0.8573 microsecond. Now, what was our tau bar? Tau bar was 2.9752 microsecond. Now the maximum delay spread will be tau of L minus 1 minus tau of 0, that is equal to 5 minus 0, that is equal to 5 microsecond. So here you can see the initial path is at 0 microsecond, but having the smaller power of minus 20 dB, compared to the rest of the components. Since the RMS delay spread weighs each delay by the appropriate power, it is not susceptible to the distortion. So this is the quality measure which measures the delay spread. So we will use RMS delay spread most of the time. So now we will solve some of the questions of the week 3 assignment. If you have any doubt, this video will be also uploaded, so you can ask. Now consider a L antenna wireless fading channel. These questions are from the previous week lectures, where HI is the fading coefficient with channel vectors. Let YI denote the received symbol on antenna I and phi I denote the phase of the HI. The output of the maximal ratio combiner is. So the output of the maximal ratio combiner is the summation of HI Basically, the maximal ratio combiner is given as summation of, not summation, that is h bar divided by norm of h. But here are ith components, so we will do for the all the ith components. So this will be our summation, and for the complex signal, here we can use the Hermitian, that is the conjugate of the transpose. So option A is the correct answer for this question. So that is also h bar Hermitian divided by norm of h into y bar. Okay. Now coming to the question number 2. Consider a multiple receive antennas with wireless channel with L antennas and HI denoting the channel coefficient of antenna for I is equal to 1 to L, and H being a Rayleigh fading channel coefficient. So the diversity of this order is, so the SNR here will be the norm of the channel into the SNR value. So this will be the complete SNR. So that is equal to their L channels with the same characteristics coefficient value. So this will be the actual SNR. So here we can write it as h squared into SNR prime. Here SNR prime is equal to L into SNR. So this is also like a single channel. This is also as a single fading channel. Just SNR is replaced with L into SNR. So it is a single fading channel. The diversity order of the system will be 1. Now coming to the third question, we have to find the approximate SNR required to achieve the bit error rate of 3 by 16 into 10 to the power of minus 8 in a wireless system with L is equal to 2 receive antennas and maximum ratio combining. So the bit error rate formula is given as 2L minus 1 CL into 1 by 2 into SNR to the power of L. So here L is equal to 2. So by substituting, we will get 3C2 into 1 by 2 SNR to the power of 2, and the bit error rate is given as 3 by 16 into 10 to the power of minus 8. So it will be 3 by 4 so it will be 2 like SNR will be here, two into 10 to the power of 4. So now SNR in dB will be 10 log 10. So this value, like 2 to the 2 into 10 to the power of 4 is equal to 10 to the power of 4.3. So this value is equal to 43 dB. So the correct answer is option number D for this question. So similarly, we will have the fourth question. Here L is equal to 3 is given. So we can substitute the value like bit error rate is equal to so bit error rate is equal to, if L is equal to 3, it will be 5 C3 1 by 8 SNR cube. It will be 5 factorial by 3 factorial into 2 factorial. So it will be 10 by 8 into 1 by SNR cube. So that is equal to 5 by 4 SNR cube. So the correct answer is option number A. Now the fifth question is on the diversity order. So we have to find the diversity order D of the AWGN channel where the received signal YK is given as XK plus NK. The transmit symbol plus the noise is the received signal. So the diversity order D is equal to minus limit SNR tends to infinite log of probability of error so this is the formula of diversity order. So for AWGN channel, the like the bit error rate is given as, we have studied the formula, like the approximate bit error rate is given as half e to the power of minus 1 by 2 of SNR. So we'll use the same here. Log half into e to the power of minus half SNR divided by log of SNR. So this can be given as limit SNR tends to infinite. Log m into n is log m plus log n. So it will be log of half plus log of e log of e to the power of minus half of SNR divided by log of SNR. So D is equal to log of half plus, it will be minus because minus half of SNR is there, divided by log of SNR. So this we can write as log half of log of SNR minus half of SNR divided by of log of SNR. Now this term will become 0 because the denominator will tends to the infinite and the denominator will be the less thing, will be less, it will be finite. So D will be, here also minus sign was there, so D will be plus of half of SNR, like limit SNR tends to infinite, half of SNR divided by log of SNR. Now this is infinite by infinite, so this can be solved using L'Hospital rule. So D is equal to the derivative of numerator divided by derivative of denominator. So it will be half divided by 1 by SNR. So this is equal to, so this is equal to infinite. So the correct answer for this question is option number B. So now coming to the question number 6. So in question number 6, consider wireless system with L is equal to 4 antenna system, and the channel coefficient H1 is given as 1 plus 2j, H2 is given as minus 1 minus j, H3 is given as minus 2 plus 2j, and H4 is given as 2 minus j. Let the noise variance is given as 1 by 4, and the transmit power is given as 6 dB. The SNR at the output of the max. So here, like, we have to find the SNR at the output of the maximal ratio combiner. So that will be given as mod of H squared by the transmitted power divided by the noise power. So if PT is equal to 6 dB, then the value of PT is equal to like 10 log 10. PT is equal to 6. So PT is equal to 10 to the power of 0.6. So this value is around 4. We can use, and the magnitude of H squared will be here. And noise power is given as 1 by 4 into 4. So the SNR at the output is given as 5 plus 2 plus 8 plus 5. So it will be 320. Now SNR at the output in dB is equal to 10 log 10 of 320. So when we find this, we will get it as 25 dB. So the correct answer is option number D. Now 3 more questions we'll solve and we will close this lecture here. So if the BR of a communication system decreases as 1 by SNR squared plus 1 by SNR to the power of 5, the diversity order of the system is. So in this question, you can see like at high SNR, the terms in the denominator having lower order will be the dominating. Let's suppose 1 by 10 to the power of 2 plus 1 by 10 to the power of 5. So what will be the value? It will be 0.01 plus 0. So this is the dominating term. So similarly, at high SNR, 1 by SNR squared will be much larger than 1 by SNR to the power of 5. So this term will be nearly equal to 1 by SNR squared at high SNR. So now what will be the order? So diversity order is equal to 2. Also we can find using the formula of minus like limit of log probability of error divided by log of SNR. So the diversity is equal to minus limit SNR tends to infinite log of probability of error divided by log of SNR. So this is equal to minus limit SNR tends to infinite log of 1 by SNR squared divided by log of SNR. So this will be minus, so SNR square will be minus 2 into log of SNR divided by log of SNR. This will be equal to 2. So diversity order is 2. Option C is the correct answer for the 7th question. Now coming to the 8th question. Given phi I denotes the phase of HI, L antenna a wireless fading channel is given where HI is the fading coefficient, YI is the received symbol on antenna I. Then the output of the equal gain combiner is, the equal gain combiner is also can be called as the maximum ratio combiner. So this is the output will be e to the power of minus j phi I into y of I. So the correct answer for this question is option number B. Coming to the 9th question. The gain G of the maximal ratio combiner where H is the channel vector in a multiple receive antenna wireless system with IID Rayleigh fading coefficient for L is equal to 4 antenna is. So the probability density of G is given as e to the power of minus g to the power of L minus 1 divided by L minus 1 factorial. So here L is equal to 4. So this value is e to the power of minus 4 g to the power of 3 by 3 factorial. So this will be 1 by 6 g cube e to the power of minus g. So option D is the correct answer for this question. Now coming to the last question of this today's lecture. Consider a wireless system with carrier frequency is 3 gigahertz. So that is equal to 3 into 10 to the power of 9 hertz. For independent fading across L is equal to 8 antenna receive system, what is the minimum length of this device? So basically D mean the minimum length of device is equal to lambda by 2. So this is the formula of the minimum length of device. So now lambda we can write it as c by fc into 2. C is the speed of light, so that is taken as 10 to the 3 into 10 to the power of 8. Fc is given here 3 into 10 to the power of 9 into 2. So this will be 1 by 10 into 2. So that is equal to 0.05 meter. So this can be written as 5 centimeter. Now there are L antennas. So L is equal to 8 here. So the maximum size, the minimum size of device is equal to L minus 1 into D min. Minimum length of antenna. This formula is for minimum length of antenna. So that is equal to 7 into 5 centimeter is equal to 35 centimeter. So option B is the correct answer for this question. So thank you for attending today's lecture, and this video is also recorded and will be uploaded on the YouTube. If you have any doubt, you can ask now and there also. So next we will meet on the Tuesday 6 to 8 in the evening in the next week. So thank you everyone. If you have any doubt, you can ask, else we can close the meeting now. Thank you everyone for joining. We'll meet on the next Tuesday between 6 to 8 p.m.